I'd like to introduce briefly the notion of a metric space and side by side the notion of a normed vector space. Or maybe it would be more accurate to say that for this audience, I would like to reintroduce these notions, which they've seen in their earlier work. Okay, so let's start with the definition of a metric space and try and map it to a diagram. So it says here, by the way, I do hope that all of this is visible. So this is the first video in what will hopefully be not a completely shambolic video series. And if it's not nice and visible, then we'll have to play around with the font size and other unpleasant aspects of video technology in today's day and age. So a metric space is any set S and a function which we call a metric, and that function is from the domain S cross S to the set of real numbers, such that this function satisfies the three properties below. The first is that if you take any two members X and Y of this set, then rho of X comma Y is always greater than or equal to 0, and it's equal to 0 if and only if X and Y are identical. The second property is symmetry, that rho of xy is exactly rho of yx. And the third property is what is known as the triangle inequality, that for every triple of points x, y, and z, rho of xy is less than or equal to rho of xz plus rho of zy. So the notion of rho is to capture some notion of distance, right? And so suppose that, I don't know whether you can see this thin red tip, but suppose this is all of space, right? So this is the first example of a metric space. The plane with nothing else defined on it. So you could say it's the Euclidean plane, right? So suppose we want to illustrate the triangle inequality. There's this point X here, another point Y in this plane, and let's say there's a third point Z. Right, so then what is being said in the third property is that this distance, rho xy, is less than or equal to the sum of rho xz and rho zy, right? So that's the triangle inequality. And if you just go by Euclid, you can use Euclidean geometry to establish the triangle inequality from Euclidean first principles, right? So we will not do that. Instead, we will treat, for instance, this example in the plane to be one where these points X, Y, and Z have Cartesian coordinates, right? And once you introduce Cartesian coordinates, you're pretty much in the domain of discussion of vector spaces, pretty much. Of course, we said that a metric space is just any set S with a metric defined on it, and a vector space, on the other hand, has a lot of structure, right? But that structure begins by giving points like X, Y, Z in the plane pair of Cartesian coordinates, right? So, let's proceed a bit further and see what more we can say. Okay. So here's the leading example, which is D2. D2, or the Euclidean metric, in the space Rk, right? The k-fold set, the the real numbers, the k-fold real numbers, right? And so the Euclidean metric, in order to define that, there's this underlying notion that each point x has a set of coordinates here in k-dimensional real space, a set of k coordinates, x1 to xk. Similarly, y has k coordinates, y1 to yk. And the metric, or the distance between x and y, is obtained by going coordinate by coordinate. So for each coordinate I, take the difference, xi minus yi, square it, add up these sums of squares of differences for all k coordinates, and then take the square root. Right? So that's the notion, that's the standard notion of distance in Rk, and it's just a generalization of the standard Euclidean distance in R2, right? So now the claim is that this is actually a metric, that it satisfies the three properties of a metric space, and you can see that indeed this distance between 2 points, D2 x comma y, will always be non-negative because you're squaring stuff and then doing other stuff, right? So it will be non-negative. When we say square root here, we always mean the positive square root, okay? So it's non-negative, it's going to be identically equal to 0 if and only if every coordinate xi of point x is equal to every coordinate yi of point y. So if and only if they're really the same point, x is equal to y, right? X is identical to y. And the third property of a metric is the triangle inequality. So it's claimed that the Euclidean metric satisfies the triangle inequality. Okay, so so if we try and write that out in full, it'll be a mess, but let's try and do that. So the triangle inequality will be that's the Euclidean distance between x and y, and it's claimed that so I is going from 1 to k, but that's understood, so I'm not going to do it every time. And so it's claimed that this is less than or equal to the distance between x and z plus the distance between z and y. Sorry. Right? So now, proofs in video lectures are somewhat tedious, and usually I'll try and urge you to sort of, follow and understand the proofs on your own, and we'll try and do only the easier stuff in the video lectures. But you're sort of used to my theater lectures, and you know that the lectures contain the easier stuff and the harder stuff is left for you to do, and that's of course a compliment to your talents, so you shouldn't take it otherwise. So now let's try and see how one goes about proving this. And one standard way is to say that, hey, let's just give these some easier names. So let xi minus zi be called ai, and zi minus bi, zi minus yi be called bi. Okay, so then notice that if I write xi minus yi is equal to xi minus zi plus zi minus yi, that's equal to ai plus bi. Okay, so then we have sort of converted the xy, xz, and zy version of the triangle inequality to this one here. Okay, on the left is the square root of this sum of ai plus bi squares. Okay, and on the right is the sum of these two, you know, the ai squares and the bi squares. So it's what's happening here. Well, it's not important that we agree on what's happening here, but in some sense you could say that, so here's my x, y, and z, and in some sense you could say that, well, what would happen now that I have a coordinate system and coordinates, what would happen if I just shift this triangle and the origin is located at x. Right, so if the origin is located at x and this xy here, so the xz here, just call it now a vector a, and this zy here is a vector b that is pulled and it's put here, right? So then this is the vector a plus b, and I can then interpret the left to be on the left hand of this inequality is the distance of the vector a plus b from the origin, and what's being said is that that's less than or equal to the distance of the vector a from the origin plus the distance of the vector b from the origin, right? So more about distances from the origin. So what's happening in some sense is that from metric spaces, you've converted this into a problem of measuring the distance of vectors from the origin. So you've converted this into a sort of vector space problem, and more about this in a minute or in 5 minutes. So now if you study this inequality a little bit, so one way to do it would be, well, suppose I square both sides and then I cancel some terms that look like summation ai squared and summation bi squared. What I'll have left on the left is twice summation ai bi, and on the right I'll have twice this product here. Okay, right? So proving that the Euclidean metric satisfies the triangle inequality boils down to proving this inequality here, right? And you can see that this inequality follows from this squared version. So if I square both sides and this inequality, this squared version of the inequality is true, then I can take square roots and say that this inequality follows, right? So if you look at this squared version, then this is just the Cauchy-Schwarz inequality, which I'm sure you've encountered earlier. And there are thousands of proofs of the Cauchy-Schwarz inequality. If you put it in this form, you can see that it sort of follows from the cosine rule. But just for the sake of completeness, the lecture notes have this simple proof of the inequality. And if you haven't followed the proof, you can talk to me. Let me just flag one or two steps in the proof rather than give the logic of the proof itself. So the proof starts with this simple inequality, which is 0 is less than or equal to this double summation of ai bj minus bi aj squared. Okay, so I take these sums of squares. That's obviously going to be greater than or equal to 0 because I'm squaring stuff, okay, and then adding them, right? So then if you open this out, you have some sums of squares of the ai bj squared, so that's this here, plus the bi aj squared, that's this here, and then you have minus 2 ai bj times bi aj, so that's this here, right? So I want to leave you to figure out the rest, but let me just make a very small comment here. There is some algebra going on that should be very simple. You can just, if you're confused, you can just open these things out using, the actual a1 squared, b2 squared, etc., right? But here's a very easy way to see how you move from this step here to the step here. And I may be saying something which is blindingly obvious, in which case you must pardon me. So for instance, take these terms here, the first term, right? So think of ai squared as a little length and bj squared as another length. So then ai squared bj squared is the area of a little rectangle whose sides have lengths ai squared and bj squared, right? And you're adding areas of lots of little rectangles, right? So for each I, I varies from 1 to k and j varies from 1 to k, right? So instead of adding these in this way, what I can do is I can take all the little lengths ai squared, right? I going from 1 to k. So that's the sum here. Sum I going from 1 to k ai squared, right? So I just add up all the ai squared lengths. Similarly, I add up all the bi squared lengths and I just multiply these two. Okay, so that's going to give me the same area, right? So I thought that's a neat interpretation, and I just wanted to share that so you can follow the rest of the proof, right? So now I want to talk about first briefly and then a little bit more in detail about this generalization from d2xy to dpxy xy. Okay, so that's here, right? So the generalization is this. So this dp notion of distance between 2 points x and y does the following. So for every coordinate I, take the difference xi minus yi in absolute value. Raise that to the pth power, add all of these up across all the I coordinates, and then take the pth root. So you can see that if I put p is equal to 2, I get exactly the Euclidean distance. On the other hand, if I put p is equal to 1, I get this sum of sort of mean differences. Okay, it's then just that, right? So the claim is that if I put any real number for p that is greater than or equal to 1, I'll have a metric. And it's easy to check that the dp metric satisfies the first two properties of a metric. And in order to check for general p greater than or equal to 1 that it satisfies the triangle inequality, generally what is used is Minkowski's inequality, and you can find a treatment in many real analysis texts, including, for instance, Kolmogorov and Fomin's Introductory Real Analysis, 1970, right? So what happens to this dp as p becomes larger and larger, right? So in some sense, what happens as p becomes larger and larger is that in this sum, the xi minus yi difference that is largest, yeah, now you're raising that to p and you're raising the other stuff to p as well, and you're adding them up. But as p goes to infinity, the xi minus yi term that's largest, that begins to dominate, right? And you can show that in some sense, as p approaches infinity, this distance will go to the maximum difference between xi minus yi, right, over all the coordinates I. Okay, because remember that these things become larger, but then you're taking the pth root. Okay, so if the max starts to dominate and really becomes the only player in town, then you raise that to p and you take its pth root, you're going to get just this, right? So that's a sort of informal claim. The point is that this itself is a metric. And that's quite easy to show, but let's show it anyway. So it's easy to see that this notion of distance will satisfy properties 1 and 2 of a metric, right? So it doesn't matter if you're taking absolute value, whether you write xi minus yi or yi minus xi, it's going to be the same. So that's the property of symmetry. And you can see that this max is going to be 0 if and only if xi is equal to yi for every coordinate, right? So if and only if x and y are the same point. In order to see that the triangle inequality is satisfied for every triple of points, notice the following. So this is the claim, right? So take any I. Take any I and measure the difference xi minus yi in absolute value terms, right? So now you can see that xi minus yi is just xi minus zi plus zi minus yi, okay? Yeah. And you can see from the triangle inequality for absolute values, which I'm sure that you've encountered earlier, that this is less than or equal to xi minus zi absolute plus zi minus yi absolute, right? But that is less than or equal to, first and foremost, the distance between x and z. So any xi minus zi in absolute value must be less than or equal to the distance between x and z, because the distance between x and z in terms of d infinity has been defined as the max across all the xi minus zi values, right? So a particular xi minus zi must be less than or equal to the max amongst them. And similarly, the second term is less than or equal to d infinity zy, right? So since this inequality, this holds for all I, it holds at the max, right? So max xi minus yi is also less than or equal to these. And what is max this but the defined distance between x and y, all right? So you can put a little rectangle here. So in some sense associated with metrics is the notion of norms. So where's the cursor? So first, let's define a norm for Rk seen as a vector space, okay? So now endow Rk with all the properties of a vector space over the field of real numbers, right? And then we'll say that a mapping or a function, blah, blah, from Rk to R is called a norm on the vector space Rk if it satisfies these three properties. And underlying the notion of a norm is that the norm of a vector is just its distance from the origin. Okay, so the distance from the origin is equal to 0 if and only if the vector itself is the origin, right? So this 0 here is the 0 vector. Right. And then the second property is that if you scale a vector by a scalar gamma and then take the distance of gamma x from the origin, that's just going to be the distance of x scaled by absolute value of gamma. And in terms of vectors, a norm satisfies this triangle inequality, that if you add up two vectors, so let me now, take this vector space. I have a vector x, not to be confused with the point x in the metric space earlier, and a vector y, and I add these up. So the resultant vector is x plus y. So if you have a proper norm, it must satisfy that norm x plus y is less than or equal to norm x plus norm y, okay? Norm y, norm x plus y. So rather than begin with a metric space, suppose we start with a vector space, which we're going to do pretty much all the time. So suppose we start with a vector space and we endow it with some norm. Whatever that norm is, that norm induces a way to measure distances between vectors. Okay, so a norm induces the metric x minus y. So what's being said is that suppose we have a vector space and we take any two vectors x and y, right? So what we've done first is we've endowed this vector space with some norm, so we know how to measure distances of these two vectors from the origin. Okay, so this is norm y, that's norm x, right? So what's being said is that consider the vector x minus y. So that's a shorthand for the vector x minus y. Or if you don't like that, take y here, multiply it with minus 1. So you get a minus y, and then you add up x and minus y, and you get the vector x minus y, right? But you see that these are just representations in some sense of the same vector displaced, right? So what's being said is that, look, the way to measure the distance between any 2 points x and y once you have the norm is you obtain this vector x minus y and you say that I'm going to take the distance of x minus y from the origin, right? So you can see that starting with the norm, when we induce a metric x minus y distance, right, it's very easy to see that that satisfies the triangle inequality, right? Well, I shouldn't say that that's so easy, but so if we want to show that this is a metric and that this satisfies the triangle inequality for metrics, well, we want to show that norm x minus y, which is the distance between x and y, is less than or equal to norm x minus z plus norm z minus y. Okay? So notice that x minus y is just x minus z plus z minus y, right? So now if you regard this as two vectors, x minus z and z minus y, and you apply this triangle inequality for norms, then it's going to say that norm x minus z plus z minus y is less than or equal to norm x minus z plus norm z minus y. Okay? So one vector space that we'll use a lot in dynamic programming is the space of all functions, all real valued functions that are bounded and that go from some domain U to the real numbers, right? So consider all functions f from some domain U to the real numbers, right? So all functions f that are bounded right? By bounded, I mean this, that f is bounded if there exists a real number k such that when I measure f of x in absolute value, that's less than k. All right, and this is true at all x in the domain, right? So consider the vector space. So the claim that we want to establish here is that if you take the bunch of all these functions and you endow this with some vector space properties, like you say, look, there is the origin in this vector space is the 0 function. That's the function that, so the origin is the 0 function. Okay, so what's that function? It says the 0 function assigns to each x the number 0, right? And you define vector addition of two functions in the usual way, which is you say f plus g of x is defined to be f of x plus g of x, and you define scalar multiplication to say that cf of x is equal to c times f of x. You can show that you've defined a vector space. So in this vector space, consider the following. It's claimed that the following is a norm. That is, for any function f, the norm of f is the sup or the supremum over all the absolute values of f of x's as x varies over u. Okay? Look at the following example. So suppose u is the closed interval between 0 to 1, and I look at all the bounded functions over this domain, right? So I can represent their graphs. So my domain is 0 to 1, closed, right? And I have all functions that are bounded, not necessarily continuous, but let's just draw a nice continuous function. So let's say I have a function that looks like that, right? So that's my graph of f, right? So now it looks to me, let me draw another function. So let's say I have this function g, right? So it appears to me that at this x, so let me call this x star. So it appears to me that norm of g is going to turn out to be, it's defined to be the sup over all g of x's as x varies over 0 to 1. So it's going to turn out that in this case it's just g of x star. Okay? So we call this the sup norm, right? So you can check that this is indeed a norm, that it satisfies the three properties of a norm. I leave that to you to check. And I define a metric in terms of this sup norm to be the following. So I say, look, whenever I want to calculate the distance between two functions, f and g, over this space, I'm going to do the following. I'm going to take the function values at each x and calculate this distance, f of x minus g of x in absolute value, okay? And then I'm going to take the max of these distances, or the soup of these distances, all right? So here's an example. So if I have these two functions, f, or graph of f and graph of y, right? And I want to know what's the distance in terms of this soup norm, right, between these two functions. So for every x, so suppose this is a particular x, right? I calculate f of x, I calculate g of x, and then I take this distance, right? I calculate the difference and I take the absolute value, right? So you can see that my distances will look like, you know, the gaps here. And it appears to me that maybe the max occurs between these two, occurs somewhere here. Call this point Z star, right? So what's this point Z star? So D infinity FG, which is the soup of these distances, f of x minus g of x, as x varies across the entire domain, visually looks to me to be this distance, right? So g of x is larger, but I'm just taking the absolute value, sorry. So the distance between f of z star minus g of z star, okay? So it's claimed that this way of measuring distances between two functions, between any two functions, actually gives us a metric on this normed vector space, right? So to check whether it gives us a metric or not, the first thing is to check property 1, which is it the case that this is always greater than or equal to 0? Indeed, it is, because I'm taking absolute values, that those are always greater than or equal to 0, right? And continuing with the first property, is it equal to 0 if and only if the two functions f and g are identical? Indeed, that's the case. If the two functions are not identical, then there is some x such that f of x is not equal to g of x, and that will give us a positive value for f of x minus g of x absolute, okay? The second property is it the case that this distance is exactly the distance between g and f? Indeed, that's the case, because if I take absolute values, absolute value f of x minus g of x is exactly absolute value g of x minus f of x for every x, right? And so it must be the same when I take the soup. And the third property is the triangle inequality. So in order to establish the triangle inequality, start with any x in the domain and consider the absolute f of x minus g of x, right? So I want to establish the triangle inequality for any triple of functions f, g, and h, right? So f of x minus g of x is just f of x minus h of x plus h of x minus g of x, right? And so this absolute value is just exactly this absolute value. This will satisfy the triangle inequality for absolute values. So this will be less than or equal to absolute value f of x minus h of x plus absolute value h of x minus g of x, right? And this absolute value f of x minus g of x must be less than or equal to the distance between f and h, because this distance is the soup over all of these as x varies across the domain U. And similarly, h of x minus g of x will be less than or equal to the distance between h and g. right? So you've established that for all x in the domain, f of x minus g of x is less than or equal to distance between f of h, distance between f and h plus distance between h and g, right? This is true for all x. Since it's true for all x, it must be true for the sup over these. Okay? So what is being said is, take all these x's and you get a bunch of these distances, right? So that's the whole set. So it's the set of all these. Right? So the functions f and g are bounded, so this is a bounded set, right? So bounded set. And so it has a sup, of course. That's the distance between these two. So when I take this, so this inequality, when we take this inequality for all x, we're saying that for every x in this set, this distance is less than or equal to this real number on the right hand side. So this real number on the right hand side is an upper bound. An upper bound on this set, right? And so the least upper bound on this set, which is exactly the sup f of x minus g of x, must be less than or equal to this upper bound. Okay? So the sup over these is exactly the distance between f and g, and therefore that's less than or equal to the sum of the two distances on the right.